In this next part of trigonometric functions of any angles, we're going to talk about periodic functions. Now, earlier in trigonometric functions of any angles, we did an example where we evaluated sine of 20 pi over 3. In order to do that, we found that 20 pi over 3 was us going around a circle 1 time, 2 times, 3 times, and then ending up a little bit out here with an additional 2 pi over 3. So we found that 20 pi over 3, our value for sine of that was going to be the same as sine of if we subtracted 2 pi, which would have given us 14 pi over 3. If we subtracted another 2 pi, we would have had sine of 8 pi over 3, and then if we subtracted another 2 pi, then we would have got sine of 2 pi over 3. Okay, so that was all from before. And essentially, if we're over here, this is 20 pi over 3, all of this. But if we subtract 2 pi, we go 1, 2, and a little bit out here, that would have been 14 pi over 3. 8 pi over 3 would have been 1 rotation, plus just a little bit more to end up right here at the same angle. They're all pointing towards that same point out here. So what we can do is we can rewrite all of these angles. We can rewrite 20 pi over 3 as, since we went around the circle 3 times, it would be 2 pi over 3 plus 3 times 2 pi. Sine, and these are all equal, sine of 14 pi over 3 would be 2 pi over 3 plus, going around the circle 2 times. So 2 times 2 pi. Sine of 8 pi over 3 would be the same as 2 pi over 3 plus going around the circle just once. So 1 times 2 pi. And then finally, sine of 2 pi over 3 is, well, we go around 2 pi over 3 plus 0 times going around. So we don't make one full rotation. Similarly, for cosine, we could get that cosine of 2 pi over 3 plus 3 times 2 pi is the same as cosine of 2 pi over 3 plus 2 times 2 pi, which is the same as cosine 2 pi over 3 plus 1 times 2 pi, which is the same as cosine of 2 pi over 3 plus 0 times 2 pi. So in general, if our angle theta is measured in radians, then for any angle theta and some point on a circle that corresponds to that, like up here, if this is our point P, then adding or subtracting integer multiples of 2 pi to our angle theta would lead to the same point on the circle. So just like integer multiples, so 0, 1, 2 times 2 pi, 3, even -1, that just tells us how many times we go around. 1 circle, 2 revolutions. If it was negative, then we go around in the negative direction. So if they all lead to the same point, then these values for sine are all going to be the same, or the values for cosine will all be the same. So in other words, what this leads to are these periodic properties. And what this states is that sine of theta plus 2 pi k is just sine of theta, and cosine of theta plus 2 pi k is cosine of theta. This is where k is any integer. So functions like these are what's called periodic functions. So we have a definition that states that a function f is called periodic if there exists a positive number p such that our function f evaluated at some theta plus that number p is just equal to the same f evaluated at that number theta. And this is for every value that we would have for theta. Now, the smallest number p that would do this, have this property, is called the period of f. So our trig functions have various periods: sine, cosine, secant, cosecant. They have periods of 2 pi, while tangent and cotangent have a period of pi. And so now we have the periodic properties. And this states that sine of theta plus 2 pi is sine of theta. Cosine of theta plus 2 pi is cosine theta. But tangent of theta plus pi, now it's just pi, is tangent of theta. Cosecant of theta plus 2 pi is cosecant of theta. Secant of theta plus 2 pi is secant of theta. And then cotangent of theta plus pi is cotangent of theta. Now, the trig identities and the reference angles can give us the values of our trigonometric functions, all 6 of them, for every angle. And really every angle from 0 to 360. Once we hit 360, it's going to be the same as 0, so we don't need to write it down here. And if we go past 360, then we're just going to use the periodic properties. And so this table, it shows us all the values between 0 and 360. Now, it may seem intimidating, but you might recognize the symmetry that we're going to get. So really symmetry that would be about 90, 180, and 270 degrees. So, you don't need to try and memorize this whole table. There are ways to get around this. So like this symmetry, if you look on either side of 90, it's going to be root 3 over 2, root 3 over 2, root 2 over 2, root 2 over 2, 1/2, 0, or then now symmetry about this line would be 1/2, root 2 over 2, root 3 over 2, 1, and then another symmetry right here, and that's the symmetry that we would see similar to the star compass. except now we have positive or negatives depending on the trig function. Sine is positive in quadrants 1 and 2. Sine is negative in quadrants 3 and 4. Cosine is positive in quadrant 1 and 4, but cosine is negative in quadrants 2 and 3. Tangent's positive in quadrant 1 and 3, and negative in 2 and 4. So these are things that can help us complete this table. We already know what sine, cosine, tangent, what the 6 trig functions are in quadrant 1, right here. And so if we use the symmetry about that, we would get the values here. Using another symmetry and another, we can get all that. And then we fill in the positives and negatives based off of the quadrant and what each trig function does in that quadrant, if it's positive or negative. Now, to get back to this, we know that the secant, cosecant, and then our cotangent, our cosecant, secant, and cotangent, they're using the reciprocal properties. They're just 1 over. Cosecant is 1 over sine, secant's 1 over cosine, cotangent is 1 over tangent. We could find tangent by using the property that tangent is sine over cosine. So really, we just need to look at these two. In fact, if we use the cofunction identity, then we know that, I recall that one says that sine of theta is the same as cosine of 90 degrees minus theta. And so sine of 0 would be cosine of 90 minus 0, or cosine of 90. We get these right here. So if we just know sine from 0 to 90, we can get cosine, tangent, cosecant, secant, and cotangent from 0 to 90. And then using the symmetry, we can get quadrants 2, 3, and 4.